Hey, good day, guys. Welcome again to my channel. And today I want to take you on the design of a steel beam section in grade 27 S275 steel in accordance to BS 5950. All right, so straight up to my screen, you see an example with which we want to walk through today's lesson. It says the simply supported beam supports a uniformly distributed characteristic dead load and imposed load of 5 kilonewton per meter each, as well as a characteristic imposed point load of 30 kilonewton at the midspan. Assuming the beam is fully laterally restrained and there is nominal torsional restraint at support, select a suitable UB section in S27 steel to satisfy bending and shear consideration. So we know what our journey is on this particular example, and it should end us at the point where we can select suitable section. All right, in we've been given the steel grade to work with, S275 steel. Okay, so this is the way we're going to go about this. I'm going to show to you step by step on how to achieve this solution. All right, so we want to begin with the analysis of this particular beam because we need to have the result of the moment, the maximum moment, as also the reactions, so that we can move ahead of this level that we are. Okay, so one of the things we have to do is to just get this free body diagram out so that we can make reference to it as we go. We have the UDL, and we've been told that the imposed load and the dead load having the same value of 5 kilonewton per meter, and this also 5 kilonewton per meter. Then at the midspan we are having 30 kilonewton. So the total length is 10 kilonewton. Sorry, 10 meter. I beg your pardon. 10 meters. All right. So we're having reaction at A and reaction at B. So let's call the midspan C. So we want to obtain the maximum moment, that is the moment at point C, looking at the fact that this B, the load, the imposed load that is subjected at that point B, point C, is at the center of the entire section. So it's going to form um, a symmetric effect on reaction at A and the support at B, support at A and support at B. All right, so what we're going to do straight up is to obtain our moment. So we want to take moment about point B. However, there are several methods with which you can obtain your moment. So whichever way you've mastered that will give you a right solution, please be free to go ahead. So, but I would just show two approaches into obtaining your moment. Then we'll move on to the design. Okay, so taking moment at B, we will have um, 10 RA. That's this force multiplied by the perpendicular distance. All right, and that's positive. That's a sign convention. So we have minus, this is an imposed load, all right, according to the question. So we want to factor in that, multiply by the factor for imposed load is 1.6, all right, and that's still the point load, multiply by the perpendicular distance to B, which is going to be 5 meters away from the midspan of this section. So we have 5 meters. Then the next, we're going to have, let's take this dead load, 5 kilonewton meters. Now factoring that for a dead load is 1.4. All right, then we might want to convert it to a point load by multiplying through with the entire span, then half the distance to B. The same thing happens with the other one, but for the fact that it's an imposed load, which we make use of 1.6 multiplied by the entire span, then the distance down to B. So resolving this, this is equals to 0 anyways. We know that this is equals to 0. So we have 10 Ra equals to 990 kilonewton. All right. So therefore, the Ra, do not forget, like I mentioned, this is equals to 0, of course, will be equals to 990 kilonewton divided by 10. That's 99 kilonewton. All right. Now, looking at what I said earlier on, that this form is symmetrical um, system that leaves our Ra and Rb to be the same, definitely our Ra and Rb will be equals to 99 kilonewton. So if you do not want to go by this way, all right, you may want to first of all get all your load types factored, all right, into a point load. This is what I mean. We already have a point load of 30 kilonewton, all right, so you want to factor it to be 30 kilonewton multiplied by 1.6. all right. You have the other one, which is 5 kilonewton dead load and life load. So converting into point load, you have 5 multiplied by 1.6 multiplied by 10, the entire span. Then the third one, you do the same thing. Point load 3 will have 5 multiplied by 1.4 multiplied by 10. All right. Now, this would give you a total of, the result will give you a total of summation 198 kilonewton. So we have the total point load, and because of the symmetrical arrangement, all right, so this is what we have. This is the 198 kilonewton at the center, is a central loading. So it means that my Ra and my Rb will be equals to half of 198, which gives us what, 99 kilonewton. So either of which way you would have your result. Now that we have the reaction at A and reaction at B, can we just obtain the maximum moment at point C, which is going to give you the maximum moment with which we are going to design this beam section. Okay, so taking moment about point C with the same sign convention which we've been working with, would have, there are two ways also, there are two ways you could do it. Let me just take you through one of the ways, and then we'll do the other one. Whichever it is you've mastered, you'll be good. So let's take the one which will be most easier, because our adventure today is not the moment, but then is to get the beam section designed. Okay, so let's take the first principle. So we have from A section of the beam at distance x that we do not know yet, all right, and the loadings that we have earlier being spelled out, QK and GK, both 5 kilonewton per meter respectively. All right, now at this point, because it is at a s distance away from the mid span where you have the point load, so that's why we do not have the point load here. Now summation of moment about x, all right, retaining our sign convention to be positive, we have Ra multiplied by x, which is the reaction we obtained earlier, all right, minus, we'll deal with the point load, the UDL, 5 multiplied by x, maybe multiplied by 1.4 because we want to factor it, the dead load, then multiply by x square over 2 to take the distance, the perpendicular distance. Or maybe I should do that again for somebody who would not get it. Okay, so having done the first one, we have dead load to be 5 and live load to be 5, uniformly distributed load on that beam. So we have that 5 kilonewton per meter multiplied by the factor, which is 1.4 for dead load, all right, multiplied by, now it's a point load. Now we're taking it down to this x, all right, multiplied by that x becomes a point load, then x over 2 to x. The same thing happens for the other one, but for the fact that it's an imposed load this time around, multiplied by x squared over 2. All right, so with this that we have done, we just want to carefully continue on the side. Okay, we have RA known already, and every other one we do not know. So when our x is equals to 0, for example, it means the moment at A will be equals to 0 kilonewton meter. All right. When our x is 5, which takes us to the mid span where we'll have the maximum moment. Okay, we'll have 5 RA. We have 5 RA minus 5 multiplied by 1.4 multiplied by 5 squared over 2 minus 5 multiplied by 1.6 multiplied by 5 squared over 2. All right, so definitely this would give us MC to be equals to 307.5 kilonewton meters. All right, so we have obtained the maximum moment to be designed against to be 307.5 kilonewton meters, and we have the shear force or the reaction to be 99 kilonewton. All right, so this exactly is the result or the result of our analysis. Now you may not need to go this far, or you may not need to do the first principle if you have a very good tool to do your analysis at this level. I have one like that. I've made a teaching on how to use the software. It's right in my channel. You can look for it and it's going to help you. Now I did that in a very simple way. This is the result of my analysis. All right, so it gave me the maximum moment with 307.5 as we obtained earlier on, and then at the support you see we have 99 kilonewton for the shear force. All right, so if you have this software or any other software that can really run your beam analysis or whatever analysis for you in simple step, you can use that. Then it makes your work faster and even better. Okay, so going back to this now, we just want to go ahead and look for the initial section selection. Okay, we want to do the initial section selection. So how do we select an appropriate section to walk through? And remember, this question already specified that we are supposed to work with 275 steel. The grade of steel had been communicated already, so we have to work with that, and we shouldn't forget. Okay, so let's go ahead. So that we'll not lose track on what we're doing, we would like to bring the question back for us to see. So the next thing we want to do is to select a section, initial section selection. Initial section selection. Okay, so and like I said, Py had already been told to us to be 275 Newton per millimeter square. That's the steel grade. The next thing you have to do is to never forget your formula, which says the moment capacity is equals to the steel grade multiplied by the plastic modulus. Okay, now we have the steel grade. We know the moment we want to design against. then we can obtain the plastic modulus from here. This is what I'm saying here, that your plastic modulus, XS plastic modulus, should be greater than MC over PY. So this will give you a guide to selecting a beam section, at least a trial section. So the moment capacity, the moment the moment at C that we obtain here is 307.5 multiplied by 10 raised by 6, then we have 275 Newton per millimeter square. Okay, so the result of this is 1118 centimeter cube. So this gives us an idea of the section we need to pick. So any section with a plastic modulus higher than this would be a good trial section for our design. Now this is the point where we would need to consult our steel section table. All right, steel designer manual, and I have a sample of that right here. So let's check. We have steel table, steel designer manual here, and we'll go under universal beam because we're designing a universal beam. Okay, so we're looking for a section that has a plastic modulus greater than 1118 centimeter cube. Okay, so looking through this, we have a whole lot of that, but I found one. Okay, let's just keep looking. Dimensional properties. You see we have plastic modulus, elastic modulus, radius of gyration, second moment of area, buckling parameters, torsional index, warping constant, torsional constant, and area of the section. Okay, so these would be parameters with which you use to design your beam section. Okay, so we are looking for one greater than 1118 centimeter cube. So looking at the plastic modulus, where do we have? Okay, we have that here. For XX, for YY, we have that. So remember, we're looking for SX. Do not be confused. You're looking for XX. Okay, so looking through this row, we have this is way higher than what we're looking for. 5638 is way higher. So you're just looking for something above 1118. So we're looking for something like that above 1118. So 1118. So we've been able to find 1810. We've been able to find 1630. We've been able to find 1450 and 1290. Okay, so because this is 1100, so we want to stay slightly above 1118, and this will be economical for us to use. All right, so we'll be using 457 by 152 by 60 universal beam. Okay, so this exactly is what we need in our design attempt. So you see how we have been able to pick our trial section. All right, going back to our design now, we want to pick that we have selected from the steel table, just like I showed to you. From the steel table, we picked a section 457 by 152 by 60 universal beam, and the XX for that section in particular is 1280 cm cube. All right, so the next thing we want to do is to classify our section, and I'll be walking you through the code of practice to do this. Okay, so we have our section classification. Okay, sorry, I want to. Okay, now when you turn to your code of practice, I mean the BS 5950 part 1 2000 in particular, you find a clause 3.5.2. So let's look for the clause 3.5.2, clause 3.5 and 5.2. Yes, this talks about classification. So the following classification should be applied. For class 1 plastic, cross sections with plastic hinge rotation capacity. Elements subject to compression that meet the limit for class 1 given in table 11 or 12 should be classified as class 1 plastic. So what's table 11 and table 12? We're coming there since it's a common reference to all of these things. So class 2 compact. Elements subject to compression that meet the limit for class 2 given in the same tables should be classified as class 2 compact. Class 3 semi-compact. Cross-section in which the stress at the extreme compression fiber can reach the design strength, but the plastic moment capacity cannot be developed. Elements subject to compression that meets the limit for class 3 given in these same two tables as a reference should be classified as class 3 semi-compact. Class 4 slender. Elements subject to compression that do not meet the limits for class 3 semi-compact given in the table references should be classified as class 4 slender. So let's just go ahead with this information and do the needful. Okay, so we want to do a classification first before we go, and that classification is what I call the strength classification. Okay, so strength classification. Now look into your code of practice. You find a table 9 from your BS 5950, and this table speaks of the strength. Yes, the strength. So let's look for the table. It will be useful for us in our venture going forward. So this is table 9. It speaks of the steel grade and the thickness, then the design strength. We are working with a steel grade. We are working with under the steel, each steel grade, we have S275, we have S355, we have S460, and there are different design strengths under each steel grade. All right, so which of them applies to the particular beam that we have chosen as the initial trial section? And that's what we want to do here. Okay, so looking at the initial trial section, the thickness T of this 457 by 152 by 60. Now let's go to the properties where the properties are 457.152 by 60. All right, so the thickness capital T right now is 13.3. You see that now, that's 457 by 152 and by 60 u beam. So you see that the thickness is 13.3. So, and that should be less than what we have here. Is less than 16. Therefore, it falls under 275. For every thickness T that is greater than 16 but less than 40 falls under 265. Greater than greater than 40, less than 63 falls under 255. So it goes and on like that. So less than 16 is less than or equals to 16 is equals to 275. Okay, so steel grade remains 275, and I hope you understand what I've just said to you in a bit. Okay, so we have design strength. Since our T is equals to 13.3, which is less than 16 mm, Py is 275 Newton per millimeter square, and that's settled, right? Okay, so the next thing we want to do is to look for to classify what I just showed to you in clause 3.5.2. We want to classify a section in that regard. So let's get to the table and see our classification. Table 11 and table 12 as recommended in the clause that we read earlier. So table 11 and 12. So this is table 11. All right, limiting width to thickness ratios for sections other than CHS and RHS. Now this would help us to classify our flange and our web. Now we're dealing with the road section anyway, so for information. Okay, so for the road section, this is a flange. This side speaks of the flange. So for the road section, we're supposed to compare the ratio of our B to capital T with all these classes parameters, and that would be able to tell us of which class our beam section falls. Now, before we go ahead, we just want to design and define what epsilon would mean in this case so that we can apply appropriately. So epsilon here is 275 over py raised power 1 over 2. So we have 275 over 275 raised power 1 over 2, and that will give us 1. All right, so we know now what epsilon is. Now going back to where we're coming from, B over T. What is B over T from our steel table? Going back to our steel table, we have B over T for the particular section we are dealing with, 457, 152 by 60. And now this is it. So B over T is 5.75 from our table, 5.75. So we have 5.75. 5.75. Now let's compare with class 1, which is 9 epsilon, which gives us 1. 9 times 1, which is equals to 9. Now B over T from this that we have just done is less than 9. Therefore, the flange is what? The flange is plastic. Class 1 plastic at that. Okay, so and that's what we have right here. That's what we have right here. So we have class 1 plastic for the flange. Now for the web. To classify the web, this we have web of an I, H, or box section. All right. So we have that which has the neutral axis at the mid depth, which is d over small t, less than the parameters for each class of steel for the web. Okay, so let's find out what d over t is from the steel table. So d over t as given here is 50.3. 50.3. 50.3. So let's get back to this and create more space. In case you have questions concerning what we've just done or what we've been doing, I would like that you drop it in the comment section. I'll be there to answer to you. And in case you're new to my channel, I want you to use the subscribe button, comment, share, like, and all you can do to make yourself good with structural designs. All right, so the d over t as seen in this is 50.3. 50.3. Now we have class for class 1, that's 80 epsilon, and that gives 80 multiplied by 1, which is 80. So since d over t is less than 80, therefore it's our class 1. Class 1 plastic. All right. Okay, so we've been able to classify our web and our flange. The next thing we want to do is to determine the shear strength, of the beam. All right, shear strength. Now the shear strength. To do this, I'll just need to introduce you to a clause in the code, and that clause would be clause 4.2.3. All right, and what does it say? Let's look for that. 4.2.3. Okay, I think I found it. 4.2.3. Okay, yes. So it speaks of shear capacity. Now the shear force FV, which we obtained earlier while we started this design, should not be greater than the shear capacity PV. All right, and the PV is given by 0.6 py AV, where AV is taken as T multiplied by D for road IH and channel sections, load parallel to web. Okay, so putting that to action, all right, so let's just put that and calculate what we have. So we have PV equals to 0.6 PYAV, all right, and where we already defined AV to be C multiplied by D. All right, so we can carefully just say 0.6 multiplied by PY. PY for this section is 275, we've been given already, multiplied by the T, the small t. Get back to this designer manual. The small t is 8.1, and the big D is 454.6. 454.6 and 8.1. 8.1. 454.6, then 8.1. Okay, so putting that to your calculator, you have 607 kilonewton. Okay, so with this we can now compare with our FV, which is the reaction, all right, that we obtained earlier was 99 kilonewton, and we were told that it should be less than PV, 0.6 PV, okay, multiplied by 0.6. So what we obtain here multiplied by 0.6, let's see if it will still be less than that. So we have 364.5. So therefore, this is a low shear load. Reading through that clause, you discover that that's exactly the recommendation. So low shear load, see that, provided that the shear force FV does not exceed 60% of the shear capacity PV. So if this is satisfied, is exactly a low shear load. All right, and that's why we're here. And because our section is our web and flange is a class 1 plastic category, all right, so we are staying with this formula that says MC is equals to PYSS. So going back to design for the moment capacity now, or bending moment, whatever you want to call it. So let me just call it bending moment. Bending moment. Okay, so we can have the usual formula I told you while we started. MC is equals to PYSS. Okay, so the moment capacity for this section, having known our PY to be 275 and our SS the one we employed to be 1190. Oh, that's not true. uh SS for this section we're using is 128. This is it. 1280. Okay, so let's just put that to work. 1280 divided by 10 over 3. So we have 275 multiplied by 1280 multiplied by 10 raised to 3. So that's going to be 352 kilonewton meter from my calculator. 352 kilonewton meters. And now the code recommends that the moment capacity should be less than, this is it. To avoid irreversible deformation under serviceability load, the value MC should be limited to 1.5 PYZ generally and to 1.2 PYZ in the case of simply supported beam or cantilever. So this is exactly what apply to us in this case. So getting back to your design, you just want to confirm what 1.2 PYZ is. Okay, and that will be 1.2 times 275. Then we'll look for the Z for the particular section we're working with. So the 457, let's go to the properties. Okay, so and that's going to be 1060 centimeter cube. Okay, so moving forward is to have our moment capacity results. Is to find our moment capacity results. So we have 1.2 multiplied by 275 multiplied by 1060 times 10 raised to 3. We have 3. This is massive. We have 349.8. 349.8. So we have this greater than this, and that seems to be a problem there. Okay. Oh, let's check through the value again to be sure that we're good. The elastic modulus X for 452 for the section we're looking for. Elastic modulus for 452. Elastic modulus for 452 by 152. Okay, 457 by 152 by 60. The elastic modulus is 1120. 1120. So that's the elastic modulus, 1120. That's what we're supposed to use. 1120. So this needs to be raised. 1120. So correcting that in our calculation, let's see what we have. We have 369, which is quite correct. So we're about making an error with the values that we used. Okay, so we have 369.6 kilonewton meters. So that means this is okay because this is less than this. Okay, to move on, we just need to calculate our moment due to self weight. Moment due to self weight. All right, we'll find the self weight of this in mass, which is kilogram per meter for that particular section we're working with. 457.142 by 2. The mass is 59.8. Okay, and that's exactly what we're going to use. So that's going to be 59.8 multiplied by 9.81, okay, divided by 10 raised to 3. Okay, and if you want to factor it as a dead load, you can do that. Okay, and so because we are looking for the moment W, this is W now. Okay, L square, the length of the beam, this is L square over 8. Okay, so we are still using a usual WS square over 8. Okay, so this value gives us 10.3 kilonewton, and this becomes the additional imposed load. So we add this to our moment obtained earlier. So total moment, we call that M total will be 307.5 plus 10.3, which will give us what? 317.8 kilonewton meters. Now we're comparing this with our moment capacity, and if it passes, then we're good. If not, we'll select another section that will be suitable for this. So moment capacity MC is equals to 3. What do we have here earlier? 352. 352. So we have 352 kilonewton meter, and it is greater than M total, which is 317.8 kilonewton meter. Therefore, the section that we selected is suitable. I hope you've been able to learn how to select correctly a beam section for your beam steel design. If you have questions around this subject or many more, you can do well to use the comment section, as I'll be there to answer to all your questions and query. And if you're new to my channel and you've not subscribed, use the subscribe button, like, share, turn on notification bell, and then we'll see you in the next video. I'm Joshua the Designer. Bye.